Hi everyone, so my name's Cathy. I'm Cathy blah blah on Twitter if you want to talk about this talk on Twitter. So Mars needs guitars in the WebAudio API, obviously because there is a guitar, and we'll be using the WebAudio API. There's been some awesome talks already about some WebAudio API stuff. Probably the main difference with this demo to most of the ones that you would have seen is that this is working with a live instrument input rather than creating your own oscillators like you would if you were making a synthesizer or some game audio or something like that. And also, most of the stuff that I'm going to show you in this talk is actually the fairly basic elements of the WebAudio API. And we're just going to do a bit of a deep dive into some of the effects that you can do and the way that the API works. So this would probably be a pretty good intro if you were going to go and do the WebAudio workshop after this. Hopefully this one will give you a bit of an idea about how the API works. And we're also going to talk about just sort of how you can kind of conceptualize the API in relation to what would happen in an actual like analog kind of real-world audio environment, because the audio API is not completely intuitive for developers. It's set up a little bit of a different way to what we're used to. So hopefully we'll kind of see how we can kind of think about the API in a way that makes sense. So the WebAudio API, it's a high-level JavaScript API for processing and synthesizing audio. So similar to modern game audio engines, you've got access to mixing, processing, and filtering, similar to what you would find in desktop audio production applications. That is from getting started with the WebAudio API, which is a HTML5 Rocks article. It's a really good article if you're interested in getting into WebAudio API. Go and check that out. But to me, this is awesome. This is the stuff that we used to kind of, try and download Pro Tools in the 90s to do this. These things cost thousands and thousands of dollars. And if you're interested in music or you're a musician or you just want to do something like this, this kind of software can be really expensive. But actually, we have the capability to do almost everything that kind of software does in a web browser, which is amazing. It's free. You can go in there and learn about how audio processing actually works. And you can create stuff for the web that anybody can see. So to me, that's pretty exciting. It's pretty cool. So it's a pro audio toolkit in the browser for free. You can connect to live audio sources. You can also create audio buffer sources from files. So you can take an audio file and create a buffer and use the buffer as the source that you're going to put some effects on or analyzers or whatever. Tone generators, so what Matt just showed you a minute ago, the oscillator, that's a tone generator. So if you need to generate your own sounds, if you're building a game or you're building a synthesizer and you actually need, you're not using an external sound, you actually need to generate it, that's a tone generator or an oscillator. It has filters, effects, and analyzers. So analyzers, they're the kind of nodes that you saw in a couple of talks yesterday that were about pulling the data out of the audio feed and being able to do something with it, being able to visualize it or learn something about the data. Effects is what we're going to look at today. And you also have filters, which I guess is a similar idea to effects. You're going to kind of change the sound in some way. And you also have access to channel mixing. So in the live environment, pretty much whatever inputs your sound card will support, you can have those inputs going into your web browser and mix them using the WebAudio API. So what we're going to build today is a basic guitar effects route. So we're going to start with the source, the guitar. We're going to apply some distortion. We'll apply a tone filter. We'll apply some gain. So gain is just a level, like how loud or soft it is. And we'll send it to an output. So that basically is this thing. So hands up who knows what that is. OK, great. So about half of you. So this is what's commonly known as a guitar effects pedal. It's a stomp box. So if you go and see a gig, or you go and buy yourself a guitar and a little amp, and the guy in the shop will say, hey, you need an overdrive pedal as well. This is the kind of thing you'll get. This is like kind of the basic one that everybody gets. And this is how it works. So you take your guitar, you plug your guitar into the pedal, you plug the pedal into your amp, and distorted sound comes out. So we're basically going to build this in the browser. And an important thing to know about an analog audio route is that if I wanted to add additional effects, so we're kind of rolling up three different kind of nodes into one thing that we're calling our guitar pedal. And you can see it's got the 3 little knobs on it for that tone, distortion, and level. But if I wanted to add more effects to my guitar route, I just plug them in series. So it's just like a daisy chain thing. The cable goes into my distortion pedal. I have another cable from my distortion pedal to my, in that case, wah-wah pedal. That's kind of makes it go wah-wah-wah. Cable going from that, and cable from the wah pedal to the speaker. So is that sort of clear that the way that you would set it up in the real world is that basically whatever effects you've got sit in a row next to each other, and they all get plugged in one to the other, source at one end, destination at the other end, sound comes out. Okay, so for this demo, I'm using a thing called Roland Duo Capture. That's that little box in the middle. I just put this picture up so that you guys can see, because it's a bit hard to kind of pick it up and show you. But that little box, it's commonly referred to as an external sound card. It basically just gives me some extra inputs that go into the computer via USB. So in this case, I can plug my guitar into the box, because obviously my laptop doesn't have a guitar jack on it. And this just gives me kind of a basic line level going into the computer so that I can do something with it. But that really is the only thing in this demo that isn't just straight web browser. Everything else that happens in a web browser, and these are about $100. And you can get bigger ones, if you want to have like 5 inputs, you can get bigger, more expensive ones that have different kinds of inputs, and you can kind of do multi-channel stuff with them. But this is just a simple one for this demo. And basically, we're going out of that to the PA. It doesn't work particularly well to use your onboard speakers. It does work, but it can be a bit laggy and sort of drops out a little bit. So generally with this one, if you're using something like this, take your output out of the box as well as going in. All right, let's code. So the first thing we need is some input. So I think everybody saw this stuff yesterday, so I won't go over it too much again. Get user media, give me audio. Get user media returns a promise. So in this case, we're just going to have a simple init audio function or an error function that just says, sorry, no stream. The next thing we need is an audio context. So we'll create our new audio context. And an audio context just gives us access in our program to all the functionality like all the sound functionality that we have in the computer. So this is kind of like our gateway to effects and sources and everything we need to use. So source and destination. So we take that stream. So we've done get user media. Get user media has given us back a stream, and we learned about streams yesterday. And so I'm going to apply the context to that and say create media stream source. So you can see that we're saying, OK, we've got some audio coming in, but our audio context doesn't know about it yet. So this context.create media stream source, that's what tells our context, yep, we've got audio coming in, and now we can do other stuff with it with context. And I also just have a little alias for context.destination, but that will be whatever you set it up to be. So in this case, I've set this up so that the output is my duo capture, and that is going out to the PA. Normally, it would be your speakers, but it's just whatever you set up as the output. Actually, I can show you guys real quick if I can get my doc. Oh. OK, basically, you just go into settings. If you go settings, sound, and you can select audio, sound, audio input, and audio output. So whatever you've got selected as your output, that's what you're getting context.destination. So basically, usually your onboard speakers. All right, so next we create some effects nodes. So the first one that we're going to do is the distortion. So we go context.create wave shaper. So wave shaper is just a type of node that we have access to. For tone, we're going to use a bichord filter, and I'm going to explain how these filters and nodes work in a minute. But at the moment, we're just sort of setting up our audio route. And for gain, create gain. So each of these is a node. Think of it just the way we saw each little effects box sitting in series. Think of each of these nodes in the same way, because that's how they work in the API. And the last thing we need to do is connect them all together. So this is the part that can be quite unintuitive, but if you think of it in that fashion of connecting A to B, and then connecting B to C, and then connecting C to the output, this is the way that they've styled the API so that it works in a similar way to the real world. So we take our source, we connect it to the distortion, we take distortion and connect it to tone, tone connect to gain, gain connect to out. So it can seem a little bit kind of tedious, but because you can have different kinds of routes, and you can have quite complex routes. I think one of the talks yesterday showed an example of an audio graph that had a whole bunch of oscillators, and each oscillator was going through a bunch of effects nodes, and then they had their own gain, and then they were being routed into gain nodes. So because it can be quite complicated, being able to represent that in code is, so the best way that you can do it is by mimicking real life. Okay, so you can think of it like this. Source is like your guitar. Where there would be a cable, you use the keyword connect. And your nodes, so your filters, your analyzer nodes, your effects nodes, are just like the distortion pedal box. And then we connect that to our destination. Our destination is like our speakers. Okay, so now that we've got that all set up, that's not actually going to do anything yet. All we've got is a bunch of nodes that just have audio going through them, but nothing's happening to the audio. And Matt just touched on this a second ago. So in order to make our sound different, we need to set some attributes. So I'm just going to show you guys quickly what this sounds like. Yeah. Okay, so this is our beautiful distortion pedal, thanks to some cool CSS from Simurai. All right, so just give you a quick demo. Okay. All right, so that's just the sound coming straight out of my guitar. There's no effects being applied yet. I've got bypass on, and I'll show you guys how bypass works in a minute. But basically what's happening at the moment is that audio is getting routed directly from the source to the destination. I don't have any of my nodes in between. So what you can hear, that is the clean sound of the guitar with no effects applied. Okay, so if we want to get some distortion happening, then we need to do a few things. The first thing is we need to apply a curve. So the way that audio distortion works, or the kind of distortion that we want to apply to our guitar, is we need to create a float32 array that contains a bunch of values, and those values look like a curve. Then what happens is we apply that curve to the waves, the audio waves coming in, change the shape of the audio waves, output the result. And that gives us this kind of clipping effect that we know is kind of traditional guitar distortion. For our tone, we're going to set the type of tone. So before we said we just want a bichord filter, there's all different types of bichord filters. So the one we're using is low pass. And again, we're going to have to calculate the frequency that we put into our low pass filter in some fashion. So let's just calculate low pass frequency. And for gain, which is our level, we're just going to set that at 0.5. So that's a slider between 0 and 1. And that's just from quiet off to full. And I'll go through how we do these in a sec. Okay, so tone. So the way the tone slider works is that a low-pass filter rolls off frequencies over a certain point. So, and you've probably seen tone controls on your home stereo. It's pretty simple. When you've got the tone set low, you'll get a real muddy low sound, and when the tone is high, you'll get like a bright, shiny sound. All that's happening there is that we're saying, okay, with all the frequencies coming in, we're going to roll off some of the frequencies at the top. So some of the high-pitched frequencies we're going to roll off. And our tone slider is just going to do a little calculation to figure out at what point we want to roll off those high tones. So when it's low, we're rolling off a lot of the high tones and we'll get a low muddy sound. And when it's high, we're not rolling off much at the top, and so we're going to get more of the high frequency bright sounds. So to represent human perception of tone needs to be calculated logarithmically. And I think someone mentioned this yesterday as well. So octaves, if you're not familiar with music, octaves, so you know do a deer, a female deer. So from the bottom do to the top do, that's one octave, okay? So one octave is like one sort of complete cycle through all the notes of the scale, and then you start again, it gets higher and higher. And the way that our perception of tone works is that there are more octaves in the low range. So mathematically, when we look at the mathematical frequency, one octave higher is not double. So if I've got middle C, C one octave higher is not double the frequency, it's calculated logarithmically. So it just means we have a little bit more of a complex calculation to do in order to make that tone slider sound smooth. Otherwise, we're going to have lots at the bottom and not much at the top. Okay, so that's what this looks like. So we're going to have a minimum of 600 kilohertz. So this says basically don't roll off any frequencies below that. So we're always going to have that kind of baseline because we don't want to roll them all off, otherwise we would get no sound coming out. So the maximum is the sample rate, and you can get that from the context as well, divided by 2. That's because the common sample rate that we're using here is 44.1 kilohertz, which is what CDs use. Professional recording equipment will be probably more like 48 kilohertz, and even kind of high-end equipment will record higher than that. But basically anything over 20 kilohertz is inaudible to humans. So that's why we want to cut off that top half of frequencies from our calculation, because otherwise our slider will be doing something and we won't be able to hear the difference because it's going to be sliding through frequencies that we can't hear. So we figure out the number of octaves logarithmically, and we apply a multiplier. And then we basically just times that by the maximum, and that gives us a frequency in between the minimum and maximum that's going to roll up and sound like it's nicely rolling up through the tones. So let's have a listen to that. So I'm just going to turn the distortion down here so that we don't all get blown away. Turn the bypass off. So bypass just means bypass my effects and just go straight from in to out. So that's off. Our power's on. Okay, we're getting a little bit of distortion because I've turned my effects on, but that's all right. Okay, so you can hear how that tone is quite low, kind of muddy. And as we go up through that tone, can you hear how that's kind of brighter? How we're getting the brighter high-end notes? If I turn it right up. I need to turn up. I can put my level up. Is that better? Sorry, this is a bit of an experiment putting all this through a PA. So, okay, but you can hear that bright tone. So if I go right to the bottom, see how it's low and muddy? Put it right at the top, more high end. Okay, so that's our tone taken care of. I'm going to put the bypass back on just so it doesn't get noisy. Okay, so wave shaper distortion. So this is kind of the one you all turned up for. You know, you want to hear some rockin' sounds, and distortion is what does it. So wave shaper distortion is how we create that distorted rock and roll sound effect that you hear on everything from AC/DC to Weezer. Now, this calculation is literally just lifted from the internet. There's this one algorithm floating around that everybody uses. And the reason is that these are quite hard to come by. So the calculation to get the values for our float32 array that represents our distortion curve are fairly closely guarded secrets by companies that build audio processing software and equipment. So like I can't really just go on the internet and say, I want to find the Boss Distortion DS1 algorithm for creating that curve. They don't give it to you. This one is everywhere. Pretty much every example that you find on the internet will pretty much use this calculation. The only number that I've changed a little bit is that x times 6 times degree. I have that a little bit lower. The version of this that you'll see on the MDN pages and in Key and Pad and everywhere uses 20 for that value. I've actually changed this to use 18 just from doing a few tests with it, but that just will jack up slightly the amount of distortion. Because most examples that you see on the net will be using an oscillator, the effect is not quite as pronounced as it is with a guitar, because the guitar is actually got like a whole bunch of frequencies going in. It's not just one simple tone. So I fiddled with that a bit just to make this sound kind of have a bit nicer, fuzzier sound. It gets quite harsh putting higher values into that. And the float32 array is the same size as our sample rate, so you can see we're going context.sample rate. That will tell me the sample rate that I'm getting from my little box. And we're saying, give me that many points on my curve. The more points you add to your curve, the higher fidelity distortion sound you get. So I could easily just say n samples of 100, and then I would have a float32 array with 100 values in it. And what happens behind the scenes is that the browser uses that as a lookup table, basically splits one oscillation of so you know how a sound wave looks like this. It would take one oscillation and apply each point equally. So I would get 100 points of change on my wave. Using this, I get 44.1 thousand points of change. And you can tell the difference. If you fiddle, if you want to plug these into a web browser, it's pretty easy with an oscillator. You can change the values and hear the difference, but you can definitely hear the difference here. If I use a low number there, I get quite a kind of gritty distortion sound. With a lot of samples, I get a nice sound. So this is what it looks like in a very basic fashion. So the values from my float32 array curve look like that. So each different curve on that far right picture is what the curve looks like for different inputs. So the flat line is for an input of 0, so basically it's not making any change to the wave. And then you can see as the input gets higher, the curve gets steeper. So the steeper we make our distortion curve, the more we're going to push our input wave to the extremes of top and bottom, and that's what's going to create that clipping sound. So the example I've got here is for a sine wave. Again, if I visualize this for a guitar input, it would not be very easy to kind of pick out what was happening because there's a bunch of frequencies coming in. But for a sine wave where you've got one single frequency, you can see how applying the curve pushes the wave into a square shape, and that's what gives us distortion. And there's actually a really cool thing on the internet called Canopy. And this is like a little WebAudio kind of playground where you can plug some values in, you can plug some code in, and visualize like what your wave looks like. So in here, basically all I've done is just paste in my code for creating the wave shaper. And instead of the guitar input, I'm going to have the oscillator. So the oscillator is just giving us one frequency. And you can see how it applies. So this is a normal sine wave. Sounds like that. Okay, that's what it looks like with the distortion on. So you can see how the wave is being made squarer. And because we're pushing more of the wave to the extremes of the top and bottom, we'll get a clipping sound, and that's what guitar distortion sounds like. So if we go back to our demo, okay, so you can hear that that's still a fairly clean sound. Okay, now I get a bit more of a dirty kind of sound. A bit dirtier again, and right at the top I'm going to get that real like, yeah? So now it's kind of starting to sound a bit more Metallica-like. Vaguely. And you can hear that the tone makes quite a bit of difference at this point, right? Where before it was just like, oh, it's a little bit muddy, it's a little bit not. But here we can hear a real difference in that sound, right? And it also makes a difference. It does get a little noisy. I think that is a combination of my guitar being a cheap, shitty guitar and this little box not being probably the most expensive one you can get and kind of an old laptop. But yeah, it's not perfect as far as sound, kind of noise reduction goes. And obviously the level just takes it up and down. Okay, I don't go through this in the original kind of what we're connecting our nodes to, but I do have to actually add a few extra things to this to make it sound not horrible. One is compression. So compression basically just squashes the sound down to make it quieter. So that distortion can get quite loud. Compression just brings it down to a kind of normal level. And the power and bypass switches just work by disconnecting and reconnecting the nodes to each other. So again, that thing of how it's just like connecting things with a cable, you also disconnect. So disconnect things from each other, reconnect. Okay, that's it. There's some further reading there. Key and Pad is really awesome, came out quite recently. That has a lot of examples. If you delve into the code, there's a lot of examples of how to create audio API effects and different kinds of filters and stuff. And there's just basically a bunch of reading there, which I won't go into, but you can check out yourself. And Canopy is really great if you want to visualize what you're doing so that you can see, you can actually see the effect on the waveform of things you're doing. That's it. Thanks very much.